Hey everyone, I'm Fernando Diaz, associate professor at Carnegie Mellon University in the Language Technologies Institute. And today I'm going to be presenting some work that I've been doing over the past couple of years with colleagues Andres Ferraro and Bhaskar Mitra on preference-based evaluation. Now, before I get started, I want to talk a little bit about me, my background, where I'm coming from, and hopefully give you some context for the rest of the presentation and my framing. So my background's in information retrieval. So information retrieval being sort of the study of things like search engines, recommender systems, et cetera. Within that field, I tend to focus on problems related to retrieval enhanced machine learning. So how do we use retrieval systems to augment existing machine learning models, as well as certain domain-specific topics like something I call tip of the tongue retrieval. And then more generally, how do we evaluate information retrieval systems or language technologies and AI more generally? The second part of my research agenda focuses a lot on the broader impacts of AI. These artificial intelligence technologies have gone from dribbling into society and production systems to widely being adopted and integrated into production systems. And as this happens, we're beginning to notice a wider set of impacts these have, externalities of the systems, in particular as it relates to culture or cultures. So if we think about things like music, how does artificial intelligence affect the creation of music through, say, generative AI technologies, or the distribution of music, for example, through recommender systems? My research on the second leg focuses on the broader impacts. And of course, there's an overlap here where I look at both of them. And so the overlap includes things like operationalizing what fairness means in ranking, or what public service media principles mean in the distribution of content. And I'm not going to be talking about that wide set of research. I'm going to be focusing on specifically today evaluation. So it's going to lean a little bit more on the information retrieval side, but I will touch on some questions of fairness that do come up, especially in the context of this reading group. All right, so let's dig in. I'm going to be using different types of evaluation methodologies, and one of the in this presentation, and one of the expressions I'm going to be using is something called metric-based evaluation. For the rest of this presentation, we're going to think about a machine learning system where we have some input to the system X, some model that I'm representing here as f of X. So it takes as an input the instance, and it generates some prediction. And normally when I do evaluation, what I do is I pass off this prediction to a human rater, who then generates some score given that's a function of the original instance plus the system prediction, right? So you might imagine this could be like a QA system where X might be the question, f of X might be the answer, then the human rater would rate the quality of that answer for that question. Okay, so this is sort of traditionally how we do human assessment of these systems. And if we look at things like summarization or generation, we can look at all sorts of different human rating systems that would elicit this sort of information, either on a single dimension like quality, or multiple dimensions as we have here. Now, increasingly, we've moved away from human evaluation or augmented human evaluation with automatic evaluation, right? So what this means is I'm replacing that thing in the middle, the human rater, with an automatic rater. And what does that mean is I'm still going to pass off this f of X tuple to the human rater, or to the automatic rater, but the automatic rater is going to have some side information. Now that side information, I'm going to be really, really agnostic about what it looks like. I'm just going to call it evaluation data, which normally we see as sort of the correct answer or something, but I'm just going to say it can be anything that helps with essentially reproducing or approximating that human rater. And at the end of the day, we have this function mu x f of x d, which computes some evaluation metric. Okay, so what is that calligraphic d? it could be sort of like in one instance a gold standard, right? So if X is for example some topic, Y or X is let's say some long document, Y is some summary of the document, and then I have a single binary value that this thing is good. I can reproduce things like perplexity or blue or rouge, where I have a single gold standard that I'm trying to approximate. Alternatively, what we can look at is something like instance rating. So if I have an XY pair and some, let's say, scalar value R associated with that XY pair, I can say that I can relax this gold standard a little bit and say I have observed a wider range of things. And this is, you run into this in production systems where I may have some censored feedback from the users. And then finally, we have what I'm going to call partial ratings, which is in cases where Y, the prediction, can be decomposed, and I can rate the actual elements of that decomposition, right? So, for example, Y might be a permutation or an entire sentence, and Y sub I might be the relevance of an item in that permutation, or maybe the quality of a specific word in the generated sentence. Okay, and these are sort of like several different flavors of what evaluation data might look like. It's not always the case that I have a Y star. Okay, so at the end of the day, what we want to do is generate some set of preferences between systems, right? So when I look at what I'm calling instance level comparison, I have two systems, A and B, and a fixed instance, okay, X. Remember, this is something like a question, and I'm asking the question, which system is better? And I want to contrast that with population level comparison, which is given systems A and B, and some sample of instances X, which system is better. Now we can rewrite this a little bit and say, the first one is looking at an individual X, and you're saying that, is the model F of A better for this X than the model F of B? And if so, I'm going to say that I prefer A to B for that specific instance X, right? And a population level comparison would say, something along the lines of, I have some aggregation over these metric values, and I want to see whether or not this aggregation over the metric values is better for A than for B. I should say that if you have any questions at all, please interrupt me. I cannot see you really, so just unmute and shout. Okay. Now, when we talk about preference-based evaluation, what I want us to think about here is a human rater who, instead of seeing just X and F of X, is seeing X and a pair of system outputs, so F of AX and F of BX, and then generating some delta here, so some preference between the two things. So delta here, you can imagine, is, let's just say, some scalar number that can be negative or positive, where negative reflects that B is better than A, and positive reflects that A is better than B. Okay, so in terms of human ratings, this is what it might look like. So here's an old paper from 2010 where the raters were actually asked to decide between these two pair of rankings for a query, which one was better. And so you see underneath the scale that goes from left to right being the best, and that would be the equivalent of my sort of going from negative to positive. You can do the same thing, not just with rankings, but with images. Say I have some text prompt for an image. I present the rater with two images, and we ask them which one's superior. And of course, those familiar with how we can train these modern large language models, preferences actually matter a lot here, because we're presenting users with a pair of, say, summaries and asking them for a preference between the two of them, and then we use that to sort of estimate the quality of the two summaries over an aggregate of a bunch of different preference data. All right, so so far, like what I've talked about is, on the metric side, human metric evaluation and automatic metric evaluation. And on the preference side, I think we're all familiar with human preference evaluation, but we're a little bit less familiar with automatic preference evaluation. So let's think about this in the context of ranking, of what this might look like. Let me just be a little bit more concrete about what we mean by ranking problems here. So I'm going to say, given some context and a collection of items, return some ranking or permutation of items that satisfies the user's information need. And here, context, I'm going to be very, very agnostic. So it could be a keyword query, question, item history if we're thinking about recommendation. Collection of items could be documents, answers, some catalog. And then satisfying the user's information need. This is where we get into this hairy question of relevance, correct answers, or sort of like, what does it mean to be good when we're designing a recommender system? Like, it could be a novel item, it could be a familiar item, it could be all of the above. And so these ranking problems exist all over the place. I don't need to tell this audience that, but it's not just web search. But I'd say I'm not going to give a number, but like some large percentage of surfaces that we interact with each day have algorithmic ranking involved in them. All right, so let me talk about what's out of scope today. What I will not be talking about. First is we're not going to be talking about graded relevance. So this is all going to be in the context of binary relevance. There is some work on graded relevance that's in the paper I described. I'm not going to be talking about multi-turn. I'm not going to be talking about delayed reward or long-term value. We won't be talking about evaluation beyond relevance, so diversity or any of that stuff. We're not going to be talking about non-list layouts that exist all over the place, and we won't be talking about data collection. Now, I know there's a lot that not talk about, that there's going to be sufficient content to talk about, but I just want to be clear that these are all things that are super, super important for us to think about when we're evaluating systems, but I'm not going to be talking about today, and we can maybe do that later on. All right, so what do we mean by information retrieval? Assume that I am some person who has some information needs. So say I'm doing a literature review. I want you to learn about some new space of some new topic. So what I might do is, from this information need, translate it into a query, step 2. And then the system, in response to the query, will generate some ranking of items from a corpus. All right, so important to note here that the system only observes the query in this case, right? They don't observe the information need. And because language is limited, I'm possibly going to have multiple information needs that result in exactly the same query. So this is where this notion of ambiguity comes in information retrieval. Now, in recommendation, I also have an information need. Now it's going to look a little bit different, but I still have this need. I'm approaching the system because I have some want or some desire that needs to be satisfied. Now, instead of it manifesting as an explicit query, it's going to manifest as some interaction history that I've had with the system in the past. Now, if I'm, say, a music streaming service, that might be the set of songs that I've listened to in the past, or a video streaming service, it could be the set of videos that I've watched to completion in the past. Again, like an information retrieval, in response to this, in this case, user history, going to generate a ranking of items from the catalog. And like information retrieval, the system only observes a history in the same way that in information retrieval, they only observe the query. And similar to information retrieval, although it looks a little bit different, you can have multiple information needs that result in very, very similar or the same histories, right? So it's not going to be languages that are going to be it's not languages that's going to be colliding, it's going to be the user history that's colliding that the system would then need to disambiguate. Okay, so what I'm calling the ranking evaluation problem is the following. So given some observed request, i.e. a query or a history, and 2 rankings, pi and pi prime, so that's the thing on the right-hand side, determine whether or not there's a preference from the user's perspective between pi and pi prime. Okay, so an important thing that we do when we're evaluating systems is to use point-wise item labels. So this is that calligraphic D that I presented at the beginning. So given some information need, what I do is I go over the entire corpus and rate each item according to how relevant or how useful it is to satisfy that information need of the user. right? So this might go from 0 to 5 if we're using, say, a Likert scale. Now, in production systems, it's important to notice that the interaction with the user is going to be where you're going to draw the rating information from. So a click you might interpret as relevance, and so you might get a +1 for a click. If you click and listen to a song, for example, you might get +5. And it's tied exactly to that specific user, right? Now, importantly here for production systems and also for non-production systems, these ratings are usually incomplete. So I don't have that information about every single item in the corpus for every information aid. I usually only see it for a subset. Now, in the context of expert annotation, so when I'm getting these ratings offline from some human raters, they're, depending on the guidelines, aggregating over multiple information needs. So they're saying, given this query that I've observed, how good is this document? And I'm going to rate it on some scale. And that notion of goodness, depending on the guidelines, might be related to the proportion of people that are actually satisfied by that document. Okay, so for example, if I have the query salsa, it might be that most people that search for salsa are looking for the recipe version of salsa, and so that might get a high grade. And let's say very few people look for salsa programming language, right? And so that might get a low grade, not 0, but it will still be lower than salsa recipe. And so that's where the sort of like these guidelines sometimes collapse all these information needs and are actually the annotator's approximation of how frequently that document will satisfy that specific information need. Okay, so thinking about metric-based evaluation, metric-based automatic evaluation, we can use these point-wise item labels to compute some evaluation metric, right? And I'll get into what that is in the next slide for a specific ranking pi, right? So these metrics can be based on, the implicit behavior in production systems or explicit behavior models in offline evaluation metrics. And we're going to say that, we prefer a ranking pi to pi prime if the metric value of pi is preferred to the metric value of pi prime. Okay, and mu here can be, these evaluation metrics have been kicking around in information retrieval community for many decades now, average precision, reciprocal rank, NDCG, etc. So let's pick apart one specific evaluation metric, which is rank bias precision. It's defined as such. So here, let's unpack the math. I'm going to use F here is no longer the model. Sorry, I've mixed up the notation, but like F here is the position of the ith ranked relevant item. Remember, I'm using binary relevance here. So F1 would be the rank position of the first relevant document. F2 would be rank position of the second relevant document if I'm going from top to bottom in the rank list. Okay, so RBP is going to iterate from the top position to the last, the position of the top ranked relevant item to the position of the bottom ranked relevant item, and use this sort of geometric discounting where gamma here is what's called the user patience parameter, right? And this form of evaluation metric has nice properties because it's top heavy. So if you get all the relevant items at the top of the rank list, you're going to have a high score, and it's the contribution of the relevant items will drop very quickly as it moves down the rank list. And so on the right hand side here, I have sort of that discounting factor for different values of gamma. Okay, but remember, we're interested in preferences between systems here. So let's spend a little bit of time looking at the difference between RBP values for two different rankings, right? And this is basically going to be the summation over the difference in these two gammas taken to the power of the specific position of the ranked item, the ranked relevant item. Okay, so that's the math on the left-hand side. On the right-hand side, I have a plot of what that looks like, where sort of the X and Y, what do they mean here? So I don't know if you can see my mouse, but one axis, I have the rank position of f of I in one ranking, f prime I in the second ranking, and up and down, you have the difference in metric value. And what this is meant to show is that outside of the cases where the rank position of the top relevant document in one ranking or the other is very high, there's going to be very, very, very little contribution to that total summation. So in other words, as I go down the rank list, the contribution to the metric difference actually evaporates, because the two relevant items are going to be so far down the rank list that gamma to that value for both of them is going to be tiny, and most of the difference is going to be taken care of from the top. Okay. Now, these top-heavy metrics, exist for some reason, right? So we believe that on average, most users, scan or pay more attention to the top of the rank list, but unfortunately, it has a couple of undesirable properties, right? So it's what I'm calling not very robust to user behavior. So there will be some users that are willing to go deeper into the rank list. Think about tasks like a literature review or something like that, where you might not give up after the first or second rank position. You might want to go down deeper, right? Now, moreover, it also has what I'm calling low label efficiency, which means that I've spent a lot of time and money collecting all this relevance information, and basically the information about the documents that are low ranked is completely inconsequential to the computing the difference between a pair of systems. And so that's not great either. So on top of this, these metrics that are top heavy are really susceptible to what I'm calling the ceiling or floor, not what I'm calling, what everybody calls a ceiling or floor effect. So basically, as systems get better and better, you're going to get more and more ties at the top rank positions. And here, the plot on the right-hand side, I have the probability of a tie between systems, according to my metric-based evaluation, given the position of the first relevant item in one of those rankings, pi or pi prime. Okay, and what you'll notice here is that if I have a really great system that has the document in the top rank position, then the probability of a tie given reciprocal rank is going to be quite high, right? So almost more than 50%, especially for this most recent Trek Deep Learning, or not most recent, but the Trek Deep Learning track from 2021. Now, this is something that's been observed in the literature and has led to a lot of people being concerned about using metrics like reciprocal rank that are resulting in these sort of like inability to distinguish pairs of systems. So returning to the ranking evaluation problem, we went on to solve this question of, given a request, whether or not ranking pi is better than pi prime. And let's focus on this idea of a preference, right? So remember that we had these interfaces that were eliciting human preferences between rankings. And there's literature that demonstrates that this is a pretty nice way to detect not just relevance, not just to predict the utility between two different rankings, but also can decompose into different aspects of those rankings as well. This is really nice work by Jin and Kim that I highly recommend reading. But these side-by-side comparisons that you have with the rankings, like they're not great, because they can, either affect the assessor, if we're thinking about an offline rater, personal preference between these things. In other words, they reflect a preference for single information need as opposed to the diversity of information needs that are coming into the system. Or if the assessor is trying to approximate, the preference for some population of users, it's subject to that assessor's bias about what that general population of users look like, right? Moreover, these are extremely expensive to run, because you not only have to bring in people, pay them, wait around, but these labels are not really gathered in a naturalistic environment, right? So you have to well, sorry, that's a separate point. You have to rerun this for every pair of systems that you're trying to evaluate. And the second sort of drawback is that these are not collected in a naturalistic environment. When we're interacting with systems, we're not interacting with a pair of side-by-side systems. We're interacting with a single interface. And so it's not clear whether or not the rating procedure actually will reflect how people will prefer rankings in production systems. Okay, so how might we drive a preference between rankings in a production system? So there's work on interleaving that was done by Thorsten Joachims in the early 2000s, which looks into how I can evaluate a pair of systems, pair of system rankings, given only a single rank list, right? And sorry, I'm going to speed through this a little bit because I just want to make sure I leave time for questions. So the way I do this is, let's say I have a given information need, ranking A and ranking B. I'm going to interleave it, which means first I'm going to initialize some interleaved ranking to empty, randomly flip a coin and pick A or B, and then pop items from A and B sequentially until I get this interleaved ranking. I will then I will present the interleaved ranking to the user and observe what documents they click on, okay? What this lets me do then is by observing and keeping track of which documents came from which rankings A or B, derive a preference or compute some preference based on what was clicked by the user. Really nice result. It's correlated with offline and online metrics. It's much more granular than these metric-based evaluations and requires substantially less data. Really nice journal paper at the bottom that I highly recommend reading if you're interested in this this style of work, where they go into many different variations of interleaving. All right, so again, interleaving, like the human rating preference evaluation, reflects a personal preference, so a single information need, right? So if I'm trying to decide between rankings A and B for a fixed query and one instance of a user interaction, I'm going to get that user's preference. Over a large population of users, I'm going to essentially compute the dominant sort of preference between these two rankings over that population of users. So if there's users that have underrepresented intents or notions of relevance, it's going to be overwhelmed by the dominant groups. Moreover, the data is relatively difficult to reuse. So this interleaving setup is really built for comparing two rankings, pi and pi prime. If you want to generalize to pi, say, double prime, you can't really do that easily. All right, so let's think about when we're developing an evaluation method, what are we looking for? So first, we would love for it to be offline, right? So we would love to be able to compare a pair of rankings without actually going to production, because that might put users at risk. It might be expensive if I want to do a lot of different evaluations, say in model development. I want it to be reusable. So I want to be able to make comparisons to entirely new systems without additional data, again, for model development purposes. Third, I would love for it to actually explicitly model preferences between rankings as opposed to going through some metrics. And finally, I want to be unbiased over information needs. So this behavior where I might get the dominant set of people's preferences represented in my preference computation is something I want to try to avoid, because I care about being robust across all possible information needs or styles of search. So metric-based evaluation is offline, it's reusable, but it also it does not compute an explicit preference. You have to bounce through the evaluation metric, and it's definitely not biased over user information needs. That was that chart I presented earlier that showed the sort of the position discounting and the near zero difference in metric value as you go down the rank list. Side-by-side comparisons, so this offline preference human stuff, it's offline, that's great. It's not reusable because each time I have a new system, I need to do an entirely new side-by-side comparison. You are computing an explicit preference, or the user's computing it for you, but it's not unbiased over information needs, right? Because it's going to be reflective of whoever the assessors are that are making that judgment. Interleaving, it's not offline. It's not reusable because I have to run an entirely new interleaving experiment for each new system. There is an explicit preference, which is great. But again, because it's a production system, you're going to be modeling essentially the preferences for the population of users that are interacting with that system. So preference-based evaluation comes to the rescue. So it is offline, reusable, explicit, and unbiased over information needs. And I'll spend the rest of the time talking about what that means. Okay, so we're going to use point-wise labeled data the same way that evaluation metrics do. But we're going to explicitly model the preference through something I'm calling a preference function, talk about later. And we're going to essentially do a uniform weighting over all possible information needs. So I'm not going to privilege people who care about the top of the rank list more than the bottom of the rank list. I'm going to say that I only care about people trying to find relevant information and try to satisfy as many of those people as possible. All right, so warm-up exercise. So imagine I have a user that's interested in exactly one relevant item, and I have these rankings A and B, where white is non-relevant, red is relevant. I would normally, in a live setting, ask this question live, just in the interest of time and technology. I won't do that here. If we ask, like, which is better, A or B, in the first box, I would say that B is better because the position of the first relevant document is higher than the second than an A. In the second pair, I have again, B is better because even though these relevant items in A have sort of like bumped up a little bit, the first relevant document is all that matters to the user interested in exactly one relevant item. And then the last one, I would say they're equal because the user interested in exactly one relevant item will find them with the same amount of effort. Now, if the user is interested in exactly two relevant items, things change a little bit. So again, in the first box, I have equality because the effort exerted to find exactly two relevant items is exactly the same. In B, or in the second box, A is preferred here because the second relevant item is in the third position, whereas in B, it's in the fifth position. So the user using B would exert more effort. And in the final ranking, again, A is better. And here, because the relevant item is, again, at the third position compared to the fifth position. So something I'm going to call the search efficiency principle is the following. So a searcher interested in exactly k relevant items, again, assuming binary relevance, will prefer a ranking where the kth relevant item is ranked higher. I mean, this makes a lot of sense, and it's probably a less strict assumption than a lot of evaluation metrics make, but I think it's not a very strong assumption, which is great. Okay, so let's pivot slightly and talk about what I'm calling pseudo populations, right? So recall that each request that comes to the system could reflect any number of possible user mindsets that they might have with respect to information needs, right? So traditionally, when we think about the sets of things that people might be interested in, we think about subtopics. So some people are looking for salsa programming language. Some people are looking for salsa dancing. Some others are looking for the recipe. Alternatively, what I want us to think about now is not subpopulations based on topic, but subpopulations based on recall levels. So what I'm calling a recall level is exactly what I've just been describing. What is the number of relevant items that the user would be satisfied by, right? So you might have one subpopulation interested in exactly one relevant item, another one interested in two relevant items, et cetera, down to the total number of relevant items. So here's an example of what this might look like. So I have some information need. And in this case, because I have three relevant items, I have three possible subpopulations, right? So the user interested in exactly one would prefer B to A, in exactly two would prefer A to B, and in exactly three, again, would prefer A to B. Oh, and that's exactly what this is. So based on this intuition, we came up with this evaluation method that we're calling recall paired preference. And it's saying it's essentially computing the expected preference over all possible recall levels user might have, right? So what this preference looks like is essentially just looking at the difference in the rank position, because that's all we were using before. That's what the search efficiency principle says, is just look at the rank position and actually don't care about the magnitude of the difference. I just care about the sign of the difference. Is the rank position of the ith ranked relevant item higher for pi versus pi prime? And that's exactly what this equation is telling us. Now we can look at the if I have some population of relevance labels, I just essentially just compute the weighted average over the positions of the relevant items. Okay, so this probability pi is you can think about it as what is the probability of a user having that recall level. And for the purpose of our experiments, we're going to be thinking about the special case of uniform, which means that, regardless of what empirically happens, like that users might be interested in only one relevant document where there might actually be 20. We're going to say, like, we care about the user interested in all 20 relevant items as much as the one who's interested in one relevant item. But of course, we can think about non-uniform versions of this. So in our experiments, we looked at different ways of computing PI based on, say, the reciprocal of the recall level or some sort of DCG-like weighting. So what we found was that first, on the left-hand side, this version of this RPP and its variance were correlated with existing metrics, which is always a good property because it means that we're capturing some things that people wanted to capture in the past. And on the right-hand side, we're using Sakai's oh shoot, what is it called? Discriminative power method to determine how sensitive the evaluation method is to detecting statistically significant differences between systems, right? And all the bold numbers in the left-hand 3 columns demonstrate that RPP family of metrics is much more able to find these significant differences between systems compared to, say, traditional metrics like average precision, DCG, or reciprocal rank. So RPP averages over all possible recall levels. So that's that uniform distribution that I was talking about before. But we can also think about specific searcher recall levels. So this is where things get a bit more theoretical and fun, in my opinion, which is I can think about a precision-oriented version of this metric that says, I'm only interested in measuring the difference in performance for searchers satisfied by at most one relevant item. And the recall oriented version of this, which is I'm only interested in searchers satisfied by when they find all relevant documents. So the M in the previous slides. Let me get into this a little bit. So what I'm calling the best case preference is when the user is interested in exactly one relevant item, right? So they don't care the position of anything and any other relevant item because they might be satisfied by exactly one relevant item. Okay, so this is I'm calling this the best case because I'm only comparing the systems at the top, and the systems, if they rank all the rest of the relevant documents at the bottom of the rank list, it doesn't matter because the user's only looking at the top position. All right, so mathematically, I'm just going to say that if the rank position of the top ranked relevant item is less than in F prime, then I'm going to say there's a preference for pi compared to pi prime. Those of you familiar with reciprocal rank, if there's a difference in reciprocal rank, I'm getting exactly the same thing. So if RR pi is greater than RR pi prime, then I'm going to say pi is greater than pi prime. Now, as I mentioned before, there are drawbacks to reciprocal rank. So the probability of ties goes up pretty quickly, and I start to get all these ceiling effects that I don't like. And so what we can do is appeal to sort of lexicographic ordering of utilities in order to compute something that's a bit more sensitive than reciprocal rank. So what I'm going to do is, when comparing two lists, if there's a tie in the top ranked relevant item's position, I'm going to back off to the second highest relevant item. And if there's a difference there, then I'm going to return that as a preference. Now, what's nice about this is over all possible positions of M relevant items in N documents, I can get a total ordering over all possible permutations. And that's really nice because it means that I don't have these ties that I'm observing reciprocal rank. So let's quickly go through an example of what computation might look like. So here's two rankings, A and B. Top rank relevant position is tied. So I'll say I can't use that to compute the preference. I'll look at the second one, tied again. And by the time I get to the third highest ranked relevant item, I'll observe that the rank position of A is lower than B. And so I would say then that B is preferred, right? And again, we observe that the sensitivity goes up a lot. So the plot or the table on the left-hand side compared to reciprocal rank shows that reciprocal rank sign lexi precision is much more sensitive than classic reciprocal rank. And then a variant on that uses reciprocal rank to reciprocal of the rank position to compute the differences is even more sensitive. And on the right-hand side, we observe that here on the horizontal axis, I have the label fraction. So that's the number of relevance labels that exist in the evaluation data set. What we're noticing is that reciprocal rank, as I get more and more labeled data, is going to get more and more tied because I'm getting the saturation of metric values at the top of the rank list, whereas lexi precision is actually getting much more sensitive as I get more relevant items labeled.
Sorry, I have a question.
Yeah,
I
go for it.
didn't fully. Do you mind going back a slide? I don't think I fully understood what you mean when you say the number of labeled items. You
Yeah,
mean
so
like 0, 1 relevance or?
it would be sort of okay, so maybe I should have mentioned this. So traditionally what we do is we say if something has you can make the raters can assess something as 0 or 1, and there's going to be a lot of unlabeled stuff, and I'm going to assume that the unlabeled stuff is 0, right?
Okay,
And
I
so
see.
the horizontal axis here is let's say I have for a fixed query in information retrieval or user in the case of recommendation, how many of those ratings are masked or removed or flipped to 0, right?
So then in the case of reciprocal rank, you're saying that it becomes oversaturated when the number of labels is very high, and
That's
then
right.
versus your metric, which doesn't.
It
Right.
goes
And
in
the
the opposite
reason for the
direction. Yeah.
yes, okay, I understand. Thank you.
Yeah,
Sorry
yeah,
about
yeah. Because
that.
we're only looking at top rank relevant position. Like I'm gonna get more and more labels, so more systems get an opportunity to be relevant and sort of collide there.
Yeah, that makes total sense. Thank
Cool.
you.
Yeah. Okay, so we talked about best case. Let's talk about worst case briefly. So we can talk about worst case in terms of recall levels. That would be the person interested in all the relevant items. That's going to be the worst case because the system has to not only find the top ranked relevant item in a high position, but even the lowest ranked relevant item has to be in a high position. Otherwise, it's going to get a really terrible metric value. All right, so that's why I'm calling the recall level M as worst case. But we can also think about it as in terms of possible relevance states. So, a system, when searchers approach a system, they're not always approaching it tabula rasa, right? So, if I'm searching for information about, RLHF, like, yes, there's a bunch of papers I've already read. And so the system should probably take that into account, or at least, if I've already read them, they're probably not as relevant as the things I haven't read. And so a conservative way to model all the possible user relevant states and when they approach a system is just to say, I'm going to look at the power set of all possible relevant states, and that's what I'm unpacking on the right-hand side here, right? So all the possible, if the user's tabula rasa, I'll recover the original relevance assessment here. on the left-hand side, but otherwise I will be flipping the relevance from relevant to non-relevant for documents or items that I've already seen. All right, all the way down to the user who has seen everything except for the bottom ranked relevant item. And I'm going to call that user the worst off user. Now, fortunately, in both cases, you get exactly the same result, which is like the bottom ranked relevant item is the thing that is the worst case, which is, theoretically convenient. And so I have this sort of notion of worst case preference, which instead of looking at F1 in terms of, and when we're looking at best case, looks at FM. So the position of the bottom ranked relevant item. And this has connections to notions of fairness, Rawlsian fairness, and robustness. Okay. Unfortunately, like the bottom ranked relevant item kind of stinks as an evaluation metric because not every system retrieves all relevant items in the top K. And so we have to assume that they're all at the bottom of the ranking, which means there's going to be a ton of ties for these systems. Fortunately, we can bring lexicographic evaluation to the rescue again and just say that, like, here assume that these two systems have the bottom ranked relevant item at the bottom position. So they're tied, and I can just basically go backwards up the rank list until I find a difference in metric values or in relevant item positions and derive a preference that way. Okay. So as before, we're observing compared to existing high recall metrics, much more statistical sensitivity. So the ability to detect these differences is much higher in legacy recall. And moreover, we're getting many fewer ties as we're getting more relevance judgments, right? So no, this is the opposite. So sorry, this is an annoying thing with these plots. Like the previous plot was left to right was more relevance on this relevance labels. This one, as you go left to right, you're removing labels. Okay. Yeah, so Lexi recalls in the first column here over a bunch of different data sets. As I remove more and more labels, you're not getting the growth and ties as high as if you were to use, say, recall at 1,000 or R precision, which both of those metrics I know are popular in both information retrieval and Rexus communities. Given what I've observed in these experiments, and given the fact that labels are super sparse, especially in recommendation, I would try to avoid those metrics altogether. I know that's a bold statement, but like I just have not seen really strong evidence that we should use them based on these experiments. Now, let me just summarize because I do want to leave time for questions. So I've spent a lot of time today talking about some back history for preference-based evaluation in general, and then the second half presenting this offline evaluation, preference-based evaluation that has these really nice properties of being much more sensitive than a metric-based evaluation. These theoretical connections to precision and recall and best and worst case retrieval, I think are interesting, and they're explored in the white papers that are on arXiv. And the other thing that's nice here is that even though I've been looking at recall levels here, this sort of explicit modeling of preferences between within user populations is potentially interesting, and you could look into, subtopical or fairness versions of this where the populations are defined by other criteria than recall level. Some logical extensions of this are, going beyond ranked lists. So this leans heavily on ranked lists. We could definitely do that, especially since interfaces these days are more grid-based. We would love to do sequence-based evaluation because we know that interactions with these systems is not just a one-shot thing, that people are, especially in search, are going back and forth. And then finally, this has been strictly an evaluation presentation, and there's an entire separate set of work is how to use this information, or how do I directly optimize for these preferences. All right, let me just wrap up there with 5 minutes to spare and can take questions now.